fabulous presentations coming up, a panel and 2 keynote speeches to take us right through to the very end. Let me kick it off by welcoming onto the stage KK Yap from Google. Are you based just locally? You just come around the corner? He didn't have very far to come in his Google car. KK, come onto the stage, and with KK, distinguished panel members, Golnaz from Fujitsu here, Rao from Fujitsu in North America, and then Shimizu-san, flown all the way in from Japan. His arms are very tired. Here he is on the stage. Thank you, panel, and good luck. I'll see you in an hour.
50 minutes.
So, hi, I'm KK. So I'm currently working at Google, so I was given a surprise that I'm supposed to say something before the panelists get to say the actual content. So what I'm going to tell you is my experience with software-defined networks while I was still at Stanford University, where we developed the technology, the protocol, and we have some exciting things that we did along the way. So I'm going to tell you a bit of history and leave you with a lot more questions, and those will be the responsibility of the panelists, basically to answer the questions that I've left behind. So that's what my talk is titled: Software-Defined Network, the Dream, the Journey, and the Challenges Ahead. So we had a dream. We had a dream, but not the Martin Luther King type of dream. And we have a dream because it was more like a nightmare. We had a problem. The academic networking community was being left behind. It was being left behind because networking ideas and networking, the practice of very networking has become so complicated that we can't really keep up. Think about the idea that would take that would change the practice of networking itself. You start with an idea, then you will actually need to go to a standards body like IETF, IEEE somewhere, or 3GPP if you are in the mobile space, and you need to prove to them that this is interesting to them, you can actually develop the protocol, it is sound, you can do this, and finally you get some deployment. And as you get some deployment, you will get some experience, and then you will then be able to feed it back to the idea, and this entire cycle of innovation takes many years and many millions of dollars. More millions of dollars than an academic community can possibly afford. So the academic community is felt that they are being left behind. They are unable to innovate. They are unable to produce graduate students that can then change the practice of networking or to take networking in a radical direction, which is really the goal of academic community in general. But if we take a look at a very different community in the same department in computer science, we look at software. Software has a very interesting cycle. Software cycle in which you come up with an idea, you stay up late for a week or so, you basically code it up, you open source it, you run it somewhere with a certain number of machines that you have, and then you might replicate it, you might actually run it on Amazon if you want scale, or Google, and then you gain experience and you feedback on that idea. This allows an idea to be implemented, deployed, experience gained, and fed back to the idea and rapidly iterated in merely weeks or months. This allows graduate students, allows the general public to actually participate in the cycle of innovation in software. So what can we learn from software in networking? So we have a dream. We have a dream of making networking more like software, to be able to radically change the direction of the practice of networking rapidly, deploy new services, change the way we manage network. Because if we could do this, we will allow students to innovate, deploy, and gain experience, and to come up with better ideas that is not only useful, practical, but also something that will actually influence the industry. In general, make the grad student actually useful and make the degree actually worthwhile, right? So we started in Stanford, we said we have an idea, we're going to make a software network. So we built a network. So what you're seeing on the slide now is the 3 buildings in electrical engineering and computer science in Stanford. This is the Gates Hewlett-Packard building and CIS. And we built a network for our own use, because if we're going to build a network, we need users, we need to be able to test that our technology actually works to some extent. So what we did is, we took 10 switches, very simple switches, mainly from NEC, 90 Wi-Fi APs that we have built from our own using Linux. And what you see there on the right is the Gates building 3D map and the position that we have put the Wi-Fi APs. And we had 2 WiMAX base stations. So yes, we ran a WiMAX service in school. It's pretty exciting to do that. And we control all this from one single server, a simple x86 server that is just 3 megahertz and quad core. And we ran the entire service and we prototype the entire thing within a year or 2 with the strength of maybe about 4 to 5 grad students. And the amazing thing is, during this time, we were going through a transition of vendors in Wi-Fi, so the Wi-Fi in the building was actually flaky, and we managed to serve many users over the period of 3 years. In fact, I was told that I was the default backup Wi-Fi provider in the building. And the network administrator is constantly hounding at me saying that you're providing too good a service, you really need to tone it down. So as we build a network, we realized that, wait, one student can innovate on the network. One student is able to deploy his service on the network. We needed more students to be using the network that we have spent the money on building and so on. So we created network virtualization. It's sort of a fancy word right here. We say virtualization, but there wasn't a very strong decoupling between our services. Instead, what we were really doing was slicing up the traffic, slicing up the network infrastructure for different students to be doing different things on it. So this was the FlowVisor project, and using this particular piece of software, because our network was software defined, it was all running within a single x86 server, we could prototype the entire virtualization platform in merely software within matters of months. So this allowed many students to actually make use of the network at the same time. And this even allowed us to conduct a class where 6 project groups basically work on the same infrastructure and is able to see their service working at the same time. So one of the things that we did with the class idea was that we took one of the ideas and then we built a demonstration around it in which we show at Genie Engineering Conference 9 2010 in front of a live audience where we actually drove a golf cart around the building and showcase how we can do different type of handovers using software-defined networks. That was an amazing project because what we essentially did is a bunch of grad students was able to actually take a crazy idea, probably not a very good one, but something that actually invoked thought, something that actually make people rethink how wireless networks should be reused, should be used and managed. We built a network that handled both Wi-Fi and WiMAX simultaneously and have a handover service that essentially doesn't distinguish between network technologies. And we were able to demonstrate it. So I think the key point here is that we're able to demonstrate ideas that can be believed to be crazy and change the thought of people in the industry and in the academic in general. So what have we shown? We've shown this works, at least in the scale of a university campus for the purpose of academic education. We can innovate very fast. We're able to conduct a class over a quarter, which is about 3 months, or you can, to be more accurate, more like 12 weeks, where you can actually get students to learn the platform, implement some novel idea, and actually see it running and actually gain experience from that class. And we can have multiple students using the same infrastructure to actually provide interesting services where they can provide to each other, right? And this idea has, as a result, been widely adopted among academic networks. There are multiple campuses as part of the Genie project that has deployed OpenFlow as their backbone, wireless with OpenFlow as some of the campus Wi-Fi for experimentation and for various purposes of running networking service. So success? Have we really succeeded? So let's come back to the problem slide, right? We had a problem. We had a problem that this cycle, it takes many years and many millions. It turns out that the industry has a similar problem. This cycle is taking too many years. Providers are not able to innovate, provide differentiating service among themselves. It's not able to actually take a networking gear deployed today and use it across multiple generations of services that they can provide. This is limiting the velocity of the industry, networking industry in general, letting a lot of software services run ahead and way forward in terms of innovation. So the industry in general has a problem. So the question is this software-defined approach the right approach for the same problem in a very, very different context in various domains like wireless, optical, and data centers? So this leads us to the challenge ahead. Can this scale? In an academic environment, 3 buildings, 100 APs, that's how it works. If you look at actual commercial deployments of thousands of APs and tens of thousands of users, can this actually work? If you look at the mobile network where you have millions of subscribers, can you actually scale this? And how? Would this be cost efficient? If I'm going to change my network infrastructure, if I'm going to evolve it to something, I want it to be economical, cost efficient, and something that I can actually not only be flexible, but I can deploy at scale. So can we actually make this cost efficient? Academic product can be a bit more expensive because we're not going to make a lot of those, right? But if you're going to make thousands or millions of those, you really need the cost to be correct. What about performance? Can we actually run at a rate that we actually care about to actually meet with the link rate that the customer expect in the next generation of networking? Not this generation. We need to perform at the level that we are in the next generation of networking. So this is where I hand it off, because I believe my job here is to ask the questions. So now the panelists will actually now provide the answers to this question. So I'm going to hand off to Gosner.
Thank you very much for attending this session, and I'm very happy to share some of the views on next generation wireless networks with you today. So the wireless technology is transforming our society. It's become a major means for communicating between people, anywhere, anytime, and increasingly also connectivity between devices, sensors, commonly known as Internet of Things. In fact, our world is becoming more and more mobile. As you see from this figure, there were around 6.6 billion mobile subscriptions in 2013, and it is expected that this number will reach about 9 billion mobile subscriptions by the end of 2019. In the meantime, the mobile broadband subscriptions are expected to grow by a factor of 4. Along with this mobile broadband trend, the mobile data traffic is increasing exponentially too. This is mainly driven by the growing adoption of high-end devices, together with users' more appetite for data, leading to about 10x increase in the mobile data traffic only from smartphones. In addition, streaming applications, the shift towards on-demand video will become more prevalent. And some estimates suggest that over 50% of the mobile data traffic will come from video in 2019. Internet of Things, another emerging sector. And the traffic from the connected objects, such as those in the smart homes, smart utility, connected car, many other applications, will increase also at an exponential rate with a projected 23x increase by 2017. So there have been several efforts to meet this demand. The wireless technology has evolved tremendously from 2G to 3G to LTE, and soon LTE Advanced will be deployed to deliver higher data rates, more capacity, and better user experience. However, with the radio link performance improvements fast approaching the existing theoretical limits, another technology solution is coming from an evolution of topology. One intuitive approach is to deploy more and more smaller base stations, something like this that you can even carry in your bag. So through the deployment of small cells, we can reuse the precious spectrum and increase the capacity of the network. And we have also developed technology that further improve the system performance, but controlling interference across different tiers of network. In parallel, in order to keep up with the growing demand, Wi-Fi networks have been heavily used for offloading traffic to ease off congestion from cellular networks. And Cisco projects that by 2017, about 46% of traffic from mobile devices will be offloaded over Wi-Fi networks. Okay. Even though these technology innovations are improving the system efficiency and increasing the capacity of the network, the challenge is that the licensed spectrum is limited. Deployment of small cells will eventually lead to too much interference. Similarly, having too many Wi-Fi devices will lead to high levels of congestion because of competition to access the unlicensed band. So the wireless industry is really requiring additional spectrum to accommodate the growing traffic demand. But when we look at the spectrum allocation in the US, it seems much of the spectrum is already allocated. But when we study more closely, it turns out large portions of the frequency in certain bands, for example in the TV band, are not being used most of the time at certain locations. So how about to use these additional bands for broadband access? Well, spectrum refarming is costly, it's a difficult process, it's time-consuming. Fortunately, spectrum sharing has become a promising approach to enable usage of these unused spectra. In the TV white spaces, the US regulator entity, or FCC, has authorized secondary access to these unused spectra, given no interference with the primary users of the band. And this is achieved through contacting a certified database. So the access point sends its location information to the database, and then the database analyzes the available list of channels for that particular location, and then sends back the list of channels. Now, obtaining additional spectrum is essential for the mobile networks. But given dense deployment of Wi-Fi networks and small cells, these spectrum bands will be likely congested as well. On the other hand, the database manager is an ideal position to coordinate access from heterogeneous networks. By regulations, every network has to provide its location information and has to contact with the database. So why not to use this central entity to provide coexistence management service as well? And we have developed an algorithm that is run in the database, and based on the information it collects from the networks, it can allocate resources more efficiently. And we show that through coordination, we can increase spectrum utilization and improve user experience. So in summary, next generation wireless infrastructure is supposed to provide much faster speeds, massive capacity, and ubiquitous connectivity. And these requirements demand a combination of system efficiency improvements and topology evolution through dense deployment of small cells anywhere, indoor, outdoor, and supporting all sorts of technology from 3G to 5G and Wi-Fi. Plus policy innovations to provide additional spectrum, not only in traditional licensed and unlicensed bands, but also shared spectrum access. It could be based on TV white space sharing model or any other model being discussed. And finally, an architecture evolution in order to enable more software-based upgrades for better management and control of network resources. So, thank you.
Good afternoon. I'll be talking about some recent trends in optical transport networks, especially for high-speed transmission, 100 gigabits per second and beyond. Everybody needs to have an obligatory traffic growth charts, but the basic message here is that the number of devices and the number of users is increasing, especially as well as the bandwidth consumed by the users. So here's a chart at the bottom left, which is actually talking about server port speeds in the cloud, in the data centers in the cloud. As you know, all of our content is residing in those servers. And the transition is actually shifting from 1 gigabit Ethernet speeds to 10 gigabit and eventually to 40 and even 100. All of this is basically driving more and more bandwidth on the core network, which is where the optical transport networks are. So when you look at the transmission capacity on a fiber on the y-axis versus time, you see this growth, which is coming from the technologies in the late 80s or so. It was mainly time division multiplexing, where you were doing sub-gigabit kind of transmission per fiber. With the advent of optical fiber amplifiers, you could do wavelength division multiplexing and go higher rates, and even up to the current state of art is 100 gigabits per channel, up to 80 channels or more on each fiber, which translates to roughly 8 to 10 terabits. And then the next step is to go beyond that to 400 gigabits per channel in the tens of terabits kind of range. All of these 100 gigabits and beyond is based on the coherent transmission technology. So when you look at 100 gigabits transport, basic idea here was to use a more complex modulation format, quadrature phase shift keying, as well as using DSP, digital signal processing, on the receiver side to basically compensate for all the impairments you have when you transmit these high-speed signals on fiber. By doing this in the electronics on the receiver, it simplifies the design and of the network design aspects of this network. So here I show some pictures where on the transmitter side you have basically a nested interferometers, and on the receiver side you have the DSP after analog and digital conversion. So each of these devices, the transmit side and the receive side, Fujitsu has in-house technologies where they have packaged them into compact modules, and the whole the transceiver, including transmitter and receiver, is being packaged into a 5x7 kind of module, and eventually reducing down in size. The next, now when you go to 400 gigabits, you run into issues with the speed of the serial electronics, the limitation on the electronics. Similarly, as you see in CPUs, where they could not just keep increasing the clock rate, they had to go into a multi-core processor architecture to increase performance. Similarly, on the optical layer, you need to have multiple subcarriers. Each may be running at 100 gigabits, but you tightly pack them so that you improve the spectral efficiency and be able to manage them as a single entity. And these kind of multiple subcarrier units are being called as super channels, and the transmission, such transmission is needed for 400 gigabits or even terabits per second channels. Here I show a picture of an optical, for example, a simple optical network. So based on the distance you need to travel, the reach you need, you could use a more QPSK type modulation format, which uses more spectrum but provides you more reach. Or if you have shorter paths, you can use less spectrum and use 16 QAM and more efficient transmission. But to do this kind of transmission where you're mixing modulation formats requiring different widths, you need to transition from the current fixed grid of 50 gigahertz to some kind of more flexible grid or spectrum assignment schemes in the multiples of 12 and a half. To achieve this programmable modulation formats, the only difference compared to the 100G transceiver is basically the addition of a digital to analog conversion on the transmit path, which allows you to do programmable modulation formats. So when you have this kind of capability of flexible grid optical networks, what kind of benefit does it bring to the overall network capacity? So here we show that on the top, we have the capacity gain versus the type of network, basically long haul network which spans across the country, or regional networks, as well as the metro, which is basically within a city or metroplex area. And you can see that based on using this adaptive modulation format to match the reach and the traffic required, you can double the capacity, especially in the metro area, because you're able to use more of the 16 QAM kind of modulation formats. But one of the challenges you face with this kind of adaptive modulation format with varying spectrum width is the usage of the spectrum is not as efficient. So you have all these blank spaces which reduces the efficiency in the network. So we proposed a hitless spectrum defragmentation procedure whereby whenever there's a traffic leaving the network, we are able to shift the wavelength without any hit to the traffic and basically create an excess increased usable spectrum to carry more capacity in the network. And I have a final slide talking about SDN for transport networks. Basically, as KK was mentioning, the initial focus of SDN was more on the packet layers as well as more inside the data center type networking. There is some focus now shifting more to the wide area network as well as including optical transport as well as wireless side of things. So why do we need SDN or what does SDN bring for transport networks? The basic benefit, as KK was mentioning, is basically programmability and a centralized way to manage the traffic or route the traffic or provide connectivity. I show here a multi-layer stack starting from the bottom, which is optical switching, OTN switching, or MPLS or IP routing. Depending on where you do the switching, typically the lower the stack you do switching, it has lower power, lower cost, lower latency, and so on. So in this kind of multi-layer networks, you would like to have a full topology view at the controller and be able to route the traffic efficiently to meet the constraints of cost, latency, and so on. So SDN can allow you to do that. The other thing is main benefit would be to improve the service agility, being able to provide or deliver new types of services or create new markets with this. So here I show a picture where you have a core network in the middle, interconnecting data centers, and you can have a single orchestrator, service orchestrator, using the SDN controller for the transport network as well as a data center controller managing the data centers and being able to efficiently transport bits across. There is some standardization on this in terms of the actual extensions needed to manage these transport nodes. Just started in Open Networking Foundation in the Optical Transport Working Group. So if you have more questions or any questions, we can visit us at booth number 10 later on. Thank you.
Okay, so I can talk about the data center network, and let's see. Is this one? Yes. So first of all, I just like to summarize the data center traffics. Currently, the problem here is the increasing traffic amount, and the traffic amount is increasing like a CAGR 30%. For 2011 to 2016. And more importantly, according to the virtualization of infrastructure, the number of virtual servers are increasing. For example, in this figure, the number of virtual servers is 3 times bigger than that of physical servers in year 2016. So, okay. So now that implies the importance of virtualized infrastructure, and especially for the importance of the network configuration in data center. In this video, by chance, the order is front, a wide area, and data center, just the same order of the speakers. So I'm just talking about the data center for the computing part. And so the number of the virtual servers is so huge, and it makes it difficult for the network configuration and management. And usually, the initial setup is the only the problem, but now reconfiguration and how to deploy the virtual systems and migrate these virtual machines from different servers to servers could be a problem. So as the figure shows, I'm not good at this one. Okay, so because of the server virtualization, it is very important to deploy the virtual network rapidly and easily. And just go back to our background. So Fujitsu Lab has a 10 years history for the development of high-speed Ethernet switches. And we have started year 2003 for the 10 gig Ethernet switches. Lau mentioned that we are still in the 40 gig phase, just started. And so the market is staying long time for the 1 gig area. And year 2009 to year 2012, we are pretty much focusing on not only the high-speed networking, but also the virtualization and how to converge these networks, basically local area networks and storage area networks. And now, finally, we starting deployed 40 gig Ethernet switches in Japanese market. So go back to the initial problem. We need to make it easy for the huge amount of traffic inside the data center. Not only for the so-called north-south traffic, but also the east and west traffic is very important. So here in so-called converged fabric switch in our product called name, we try to deploy high-speed, large-capacity Ethernet fabric. And here we implemented with mesh connections between switches with redundancy and also the link aggregation kind of the fault safe mechanism. And that gives you a great performance between servers and between storages, but still you need connections to the routers. So for the routers, we have a data center core network, and this could be managed by the other network administrator. So we have more focusing on this server side or server edge networking, so that easily we can deploy the virtual machines. And that is kind of our first motivation to try the software mechanism into networking. And one of our features in the converged fabric, we have a virtualized fabric for slicing. KK mentioned about the slicing for the campus area network. And here we have a similar thing, but more focusing on the multi-tenancy. Virtual machines makes a group of virtual runs, and it could be deployed per tenant. And also, we introduced an automated migration of profiling mechanism in the network. Okay, here. So when the virtual machine is migrated from this physical server to this physical server, the networking fabric can easily chase the configuration and automatically reconfigures the network to the DC core network. These features are implemented in fabric firmware. So in that sense, I'm sorry, KK, this is not a centralized control approach. But there is a reason for this. Because for the enterprise system, we need lots of robustness and manageability. And so that's why we choose these mechanisms relatively in a conventional scheme. because so that we can change the route very quickly, and also it makes us possible to make it visible the existing paths. So that's why we picked up the existing multi-chassis RAG technologies as base of the redundancy. But in here, we are demonstrating one of the SDN-based approach in the booth, and this is based on the storage area network. There's a technology called fiber channel over Ethernet that integrates fiber channel traffics on top of the existing Ethernet. And in this case, when we want to introduce SDN flavor in the system, the typically storage area network is outside of the scope of existing open flow. So we added the management mechanism and APIs to the firmware of the Converged fabric experimentally, and successfully demonstrated that these storage area networks can be managed by the existing controller. So this is the contents of the Exhibit 6, storage flow operation using SDN. And we here, in the local switch, we picked up the storage traffics by the switch itself and sent to the external controller. And this controller can optimize the storage traffics based on the information gathered through the entire network. This could be exactly or almost the same as the open flow concept. And so we can have successfully demonstrated that these our idea successfully works in our environment. So go back to the KK's initial slide. We have successfully demonstrated. We got idea, we got experiment, and rapidly demonstrated it works. So that's the current status. So in summary, currently we have in my personal opinion, we still have a hybrid, so-called hybrid approach is useful or practical in a data center network. You can use the SDN approach on a more higher concept, but still in the lower side, we can use our more existing robust technologies. I think that's my positioning. Thank you.
This. So, is this on? Okay. So now we are running into 10 minutes, so we can actually get a question from the audience. We can go directly into that so that you get a chance to ask your question, or I can ask them easy questions. So, any volunteers? Gentleman over there.
Software-defined networks versus NFV, network function virtualization. So where do you see that fitting in some of the things you had just mentioned around the server and FCOE sort of aligns a bit with network function virtualization. So I'm curious, how do you see that happening, and do you see network function virtualization entering into the WAN and not just the LAN?
So let me generalize the question for all three domains in terms of optical, wireless, and data center. Maybe each of you all should. I think Sumiji start.
I think a network function virtualization is a concept, what you want to do. And on the other hand, software-defined network is a method to achieve this. So it is a complementary position for this. I think you need SDN approach in order to achieve NFV.
Any comment from Raul?
Yeah, I mean, as he mentioned, it's complementary. Basically, the virtual network functions will be deployed in the data centers on the servers. How do you link them? How do you service chain them is what SDN would do, help there. In terms of the NFV functions, I mean, I don't see the optical layer being virtualized, but more of the packet high, DPI, deep packet inspection, those kind of deep packet processing kind of functions at least will be the initial kind of functions which would be virtualized.
Rosna, any comment?
I also share the same view that NFV and SDN are complementary. So you can have NFV or SDN without each other. In terms of wireless domain, we can have virtualization of some of the functionalities, such as load balancing or radio resource management. But again, you would require some sort of SDN controller to link everything together.
Do we still have a question from the audience?
So this question is actually not about technology, but about policy. There was a recent decision on net neutrality, so I just wanted to see if anyone has any comment on that. Do you think the court decision will stand or not? And any other comment around this issue that you want to make?
So I'm going to try to rephrase the question slightly to sort of fit into the theme a bit more interestingly. So if you think about the ability of SDN is basically to provide flexibility and programmability, do you see a role in both optical transport, data centers, and because of multi-tenant, and in wireless, to basically enable the user to make deeper choices about how they use their network so as to circumvent this network neutrality thing, right? Because if the user is the one making the decision, there's no neutrality to talk about. I, as a user, have decided to choose a service over another, so the network provider no longer get into the game. So what do you think about that general approach, or how do you think this entire infrastructure that we are developing today is going to play out in that business environment and policy environment of net neutrality?
So I think it depends on the definition of users actually. So who you are talking to is an infrastructure manager or end user. And to me, I can say about the infrastructure is a more closer user for the data center infrastructure. So in this case, again, so the goal is a little bit ahead in terms of your question. Because the user's requirement falls down into the infrastructure requirement and goes down to the real implementation. So in future, we are looking for accommodate these requests down to the infrastructure. But currently, this is a future work or research topic, and we try to do this.
So I guess, more on net neutrality portion. I believe, as you know, most of the service providers are basically right now losing money by all these over-the-top kind of services, like Netflix and so on. There may be some, if there is, they're trying to find ways to generate more revenue, and maybe this would give them that option. In terms of actually whether it will be stayed or whether, I'm not sure about the actual regulation side of it.
Yeah, exactly. The SDN architecture enables more flexibility, so some control can be shifted towards the user to manage what they want to do. But at this point, it's not very clear who is going to own the infrastructure, whether the network operator or the user. But certainly, the flexibility will be there for the user as well.
So I'm looking for a quick follow-up before I ask the question from my own deck. Okay, let me ask the question of, one of the hope of the new network infrastructure in general is that the trend is that traffic is increasing, and we want a more programmable, a more flexible network infrastructure in general. So one of the hope of SDN is to push the complicated business logic out of the box and make gears cheaper and cheaper. So how do you think that will play out each of the domain in terms of data center, optical, and wireless? In terms of if the vendor now has to sell triple gear, how do they actually adapt to this new business environment and new technology at play? So let's go the reverse this time now, okay. Just to push musician on the spot, but what's nice?
I'm sure. Well, actually, it provides a great opportunity for mobile operators. As I discussed, the wireless network operators are turning into deployment of more and more small cells. And with close deployment of small cells, the chances of interference are going to be higher. Now, the current solutions that we have in wireless, they are not going to scale, or they are going to drive up the complexity and the processing overhead for such a massive, large-scale small cell deployment. Now, with SDN, we can push all the processing to the cloud, and with a global view of the network topology. So the resource allocation can be better managed based on the profile of each base station, based on the demand, the load, and the resources available. Another significant challenge, as you also mentioned in your presentation, is to deliver seamless services over and across different technologies. And again, the vendors can take advantage of the centralized controller to position or reposition the traffic based on different channel conditions, such as congestion levels or available bandwidth or user experience. So definitely it is beneficial, even though that the hardware is going to be cheaper, but because you're going to be independent from your hardware and do any software upgrade fairly quickly, it will help with both vendors and operators.
Rob?
So in terms of optical transport systems, there's a lot of challenges in terms of it's actually a complex system to design, especially because the transmission is in the analog domain. And there are a lot of impairments, and each system vendor usually have some unique and proprietary methods to overcome some of those impairments. For example, the DSP I mentioned, the algorithms which are used inside to compensate for the impairments are usually proprietary. So it's, even in current transmission systems, for example, even at 10 gigabits, or for that matter, even 100, there is no interoperability between system vendors. So it's very hard, really, to create a white box kind of equivalent for the transport system, at least in the near future.
Okay, so for the data center, I think well, currently we are doing this networking system not for the network switch itself, but it is for the method to integrate systems into server and storage and network into one big domain, and so in that sense, we can use as much as we can if it is available for open source for example. And but the problem here is what we can build on top of this system. And as I mentioned in slide, it is okay if it can be utilized by the open source or SDN approach. But if it is not, then we should do this. So that could be a additional value for the company like Fujitsu to provide the end customers.
Okay, I believe we're out of time, and so assuming no one has any really urgent question, let's thank the panelists for letting us putting them on the spot.
Thanks everyone, thanks for coming up onto the stage. I'll let you all get off. Hundreds of you pouring off the stage.